Hello everyone, my name is Achinta Kundu and I am currently a postdoctoral researcher in the Center of Multidimensional Spectroscopy and Dynamics, Institute of Basic Science and Department of Chemistry at Korea University. We would like to present to you our recent work that was published in JPC Letter entitled Water Hydrogen Bonding Network Structure and Dynamics at Phospholipid Multibilayer Surface by femtosecond mid-IR pump-out spectroscopy.
The profound understanding of water dynamics at the biological interfaces, such as lipid membranes, is an important issue in modern science. In particular, it is important to study water-hydrogen bonding structure and dynamics as a function of the structure of a membrane. In this picture, the left and right represent the gel phase and the liquid crystal phase of the lipid multibilayer, respectively. The phase transition from the gel phase to the liquid crystal phase can be realized by changing temperature. Depending on the temperature, the packing of the lipid bilayer will change. At lower than phase transition temperature, all the lipid molecules are closely packed and the hydrophobic chains are fully extended. On the other hand, at higher than the phase transition temperature, the lipid molecules are not fully extended anymore, surface area increases and bilayer thickness decreases. Here we employed femtosecond mid-IR pump probe method with HOD infrared probing to study the water-hydrogen bonding. As a model system, we studied multibilayer form of 1,2-dimeristyl SN glycerol 3-phosphocholine, here DMPC molecules.
Left-hand side figure shows the linear absorption spectra at DMPC multibilayer by red lines and in isotopically diluted bulk water by black lines. The solid and dashed lines are the spectra at 288 and 318 Kelvin respectively. The absorption spectra of OD stretch mode in the DMPC multibilayer are indistinguishable from that in the isotopically diluted bulk water. The main spectral feature with increasing the temperature from 288 Kelvin to 318 Kelvin is blue shifting of the peak position. This indicates the reduction in number of hydrogen bond or weakening of the hydrogen bond network in the DMPC multibilayer. The following figure shows the isotopic IR pump-up spectra of OD stretch of HOD in the DMPC phospholipid multibilayer at 288 Kelvin and 318 Kelvin respectively. The IR pump-up signal shows both positive by red color and negative by green color at the earlier times, and there is only positive signal at later time. The positive signal in the IR pump-up spectrum correspond to the ground state bleach and stimulated emission, that is 0 to 1 transition, whereas the negative signal is due to the excited state absorption, that is 1 to 2 transition. It is clear that the signal on the lower frequency side decays faster than that on the blue side, which indicates at least two different vibrational lifetime component is there. We have analyzed the IR pump-up spectra with a model which takes into account the effect of growing heating component and two decaying components as reported by Bunker's group. We show here the total IR pump-up spectra at 0.4 picosecond by black circles at the corresponding eigenspectra of the two decaying component, that is component 1 by red color and component 2 by blue color, and the heating component by green color at 288 Kelvin. The peak position of component 1 is redshifted with respect to that of component 2. In the below figure depicts the temporal profile of component 1 and component 2 at 2500 cm inverse. Component 1 decays much faster than component 2 and its vibrational lifetime is 0.6 picosecond, whereas that of component 2 is 1.9 picosecond. The center peak position of component 1 is at 2490 cm inverse, which is much lower in frequency than that of HOD in isotopically diluted water. Furthermore, its line width is narrower than that of bulk water. Thus, component 1 is assigned to the water molecule associated with phosphate group of the lipid. The vibrational lifetime of component 2 is close to that of bulk water. Therefore, component 2 is the spectrum of bulk-like choline-associated water. The center peak frequency of component 1 spectrum is significantly blue shifted, that is from 2490 cm at 28 Kelvin to 2520 cm at 318 Kelvin. And its temperature dependence shows a sigmoidal pattern as shown in figure A. As temperature increases, the surface area of lipid bilayer increases and more water molecule can access the phosphate part as multibilayer undergoes gel to liquid crystal phase transition. Figure B exhibits the dramatic change of the relative fraction of two different type of water molecule upon the phase transition, which are extracted from the integrated area of pump spectra with the assumption that OD transition dipole moment is approximately frequency independent. This strongly shows that the redistribution of water hydrogen bonds occur at phase transition point, though the hydrogen bond strength of OD with phosphate group remain the same. Note that the supporting evidence for this statement will be discussed in the later. More specifically, the sigmoidal change of component 1 peak frequency with increasing the temperature indicate either reduction of the hydrogen bond number around the HOD of HOD-OP complex or weakening of the corresponding hydrogen bond.
The following figure shows the two vibrational lifetimes, tau1 of component 1 and tau2 of component 2, and that of the OD stretch mode in isotopically diluted bulk water at different temperatures. The vibrational lifetime of component 1 is constant throughout the temperature range. The vibrational lifetime of OD stretch in isotopically diluted water is barely temperature dependent in this temperature range. But the vibrational lifetime of component 2 is constant below the phase transition temperature and then changes in sigmoidal fashion with phase transition at 307 kelvins. The dominant pathway of the vibrational relaxation of the OD stretch mode is through the overtone band of an asymmetric phosphate stretch mode. As schematically shown in insert figure, the vibrational density of states of the overtone band of asymmetric phosphate stretch mode overlaps with the component 1 spectrum, which might lead to the very fast vibrational relaxation of component 1. The fact that the vibrational lifetime of component 1 is constant throughout the experimental temperature range, even though component 1 is blue shifted with increasing temperature, can be explained by noting that the spectral overlap between the component 1 spectrum and the vibrational density of states of the overtone of the asymmetric phosphate stretch mode changes little as the asymmetric phosphate stretch IR spectrum is independent of the temperature. The vibrational lifetime of component 2, tau2, is constant below the phase transition temperature, but it suddenly increases at 307 Kelvin. Above this temperature, tau2 gradually increases with increasing temperature. Below phase transition temperature, because of tight packing of the head part of the lipid in the gel phase, mainly bulk-like water around the choline contributes to component 2, and the vibrational lifetime is indeed close to the bulk water. As temperature increases from 303 to 308 Kelvin, the vibrational lifetime tau2 jumps from 1.9 to 2.3 picosecond. This sudden increase of the vibrational lifetime has not been observed before. With increasing temperature, a lipid phase transition from the gel phase to the liquid crystal phase occurs. Because of the concomitant structural change of the lipid bilayer, the water molecules near the more hydrophobic choline part contribute to component 2. This might be the reason that the vibrational lifetime tau2 shows a discontinuous jump at the phase transition temperature. The increased vibrational lifetime with increasing temperature beyond the phase transition temperature can be explained by the heating effect of the water dynamics.
In summary, we use the femtosecond mid-IR pump-up spectroscopy to study the water structure and dynamics at two different phases, that is gel phase and liquid crystal phase of aligned phospholipid multibilayer systems. We observe two very different vibrational lifetime components at each phase of the lipid multibilayer. The fraction of the amplitude of these two components is changing with phase transition. The lifetime of component 2 shows the phase transition behavior. I would like to acknowledge IBS for supporting this work. All the IR pump-up measurements were performed by using the multidimensional spectroscopy facility in the Seoul Center of Korea Basic Science Institute. Finally, I would like to thank all of my lab members and thank you very much for your attention.